Okay, so we want to take the wisdom we have from quantum mechanics and then apply it to field theory, right? About when we're thinking about renormalization. So in quantum mechanics, what happened was that we only ever encountered these infinities when we did something very particular, which was we restricted our attention to a low energy or long wavelength subsector of the theory, right? We asked, so we have some short range potential. We don't understand its detailed form, but we're not that interested because we're scattering some very long wavelength modes off of it, right? And we were interested in calculating essentially reflection and transmission coefficients or the scattering amplitude in this simple example. And all we needed to understand was sensitivity to the short distance physics, like what parameterized the sensitivity to the short distance physics. And that was captured by the coupling constant. All right, so the coupling constant in this context came actually from some multipole expansion of this short range potential. Right, the multipole expansion takes the short range potential, gives you a series of distributions, right, delta function like distributions, and those have coefficients, and those coefficients are the things that we would tune. Well, okay, let's not say tune. They're the ones we would go and measure, in fact, right, to peg to a value. And then our theory, with our knowledge of renormalization, will tell us how to extrapolate this to longer or shorter wavelengths, right? Scattering something with a longer or shorter wavelength. So that's all really cool. Now, in quantum field theory, the first conceptual difference is that you're always essentially in the situation where you're scattering modes of some sufficiently long wavelength off of your potential. That's the key claim. In textbooks, this is a claim that comes at the end, and you have a procedure that precedes it. A procedure involves these infinities, and then you do some subtractions of infinities, and it looks very strange. But the truth is that you're just always in this situation, except for the case when you have what's called an asymptotically free theory or something. So it depends on the flow, but by default, you just assume that I only really have knowledge above some energy scale or above some length scale, below some energy scale, above some length scale of what's going on. Right. So we want to interpret everything that we do from that context. So that's a basic premise. Now let's pick some theory and some divergence. So we said that we'll start with the diagram and go through what this usual procedure is. I think the simplest thing to do is take phi 4 theory in 4 dimensions. So briefly, what's the Lagrangian? Well, it's this. I'm just gonna. Okay, so let's share my screen in a second. Sorry. Yeah, Mathematica is a bit slow today. But I mean, if any of you guys have want to volunteer to do the the writing for us, I'd be down.
Sure, I would do that. No problem.
Okay.
Wait, I think
Just
on
So,
Mathematica, right?
or whatever. I mean, if you have some convenient drawing tools and you can follow what I'm trying to.
yeah, I have a digital screen, so
Oh, that's nice.
Okay.
But
yeah,
I mean, I think I can take over shortly, just because Mathematica is slowly coming to life, and we'll need a few things.
no issues.
Mm-hmm.
Yeah. Okay. So let's, you know what, let me start without Mathematica for the time being, and then I'll just steal the images from other places
That's fine.
because I don't need to really draw all of them. These are
Yeah.
pretty standard things. Okay. So you guys can see my screen now. Cool. So what I have is, well, apologies. Great. So we have Lagrangian. Which is given by don't know. So we have a kinetic term with the normalization of 1/2. So for reference, why do we never put an arbitrary coupling constant here? I mean, we could, but the idea is that we're sort of measuring scales with respect to the kinetic term. And that's because we have this picture of weak interactions where everything is a perturbation on top of the free theory, at least, you know, for time being. So we keep this normalization to be a half. Now, of course, if you have wave function renormalization, right, that's going to show up here. For now, let's not worry about wave function renormalization. In the theory that we're dealing with, this only appears to at two loops. So I don't have the stamina to go through that calculation. 24. And what's more, let's call these bare coupling constants. Right. So when we say bare coupling constants, then we have a sense that these are the couplings that we're setting in the ultraviolet, right, at the short distance scales that we call our cutoff. Again, think back to what we did in quantum mechanics, right? So now we'll proceed by looking for diagram we can draw, right, which will encounter some trouble. So let's see. I think that my signs are a bit off for this to be a Lagrangian, but now they're fine. Okay, so you were talking about these 1pi diagrams. Does anyone remember why we define them and where we define them?
Define them. So is the idea that like any diagram which has like which can be cut in the middle without like splitting it up, we can get any other diagram by multiplying a bunch of them. So talking about
Right.
one PIs is just basically the most convenient option.
Yeah, but it also is the natural set of diagrams that appear when you're expanding the this quantity. So if you
Oh yeah.
remember, there's this thing called the effective action.
Mm-hmm.
Um, so this is a bit of formalism, but yeah, but basically it's related to the partition function in a particular way. So it is minus, and then you have something that goes like this. You have phi partial j of phi with respect to phi. So it's sort of your exercise to figure out what all this is, what's going on here. For now, it
Motivation for
doesn't
this
matter too much.
definition.
Yeah, so sorry, this is partial j of log z, I think. Something like this. Yeah, I can't really remember now, but basically there's some Legendre transform of this thing, and we can go some other day and figure out why we need to do all that and why that quantity captures these 1pi irreducible, one particle irreducible diagrams and so on. But as Shireen said, say we had a Feynman diagram. Let me just look up an arbitrary Feynman diagram on Google Images, and we can ask, how do we cut it, right? So first of all, do we remember what the Feynman diagrams are in the first place? Like, what exercise that we did uh, captures the thing we call Feynman diagrams. We've done a version of the exercise that.
I
Was
guess
it the Dyson formula thing?
Yeah, exactly. It's the Dyson series that we were dealing with. So what we do from here, we extract the interact, and we just try to expand that. We try to expand the S matrix, and as you can remember, there are two things we would need. Number one, the propagator, right? The Feynman propagator. The propagator associated to the free part, that is these two terms. And number two, we would need the matrix elements of this interaction Hamiltonian, right? And then we can build up our Dyson series. So the various terms appearing in the Dyson series are the Feynman diagrams. So next time we could dedicate a day to just figuring out how that works, right? Talking about Feynman rules and so on, because we have enough background to do this well, I think. Um, so let's see. Let's find convenient Feynman diagram that has a number of loops and things so that we can cut it. So out of curiosity, the logo, the CFRC logo, is that 1PI?
it is.
No.
No. Oh.
Because there's two vertices, a loop. So really you'd cut off the two vertices, the
Right.
cubic vertices, and you'd have the loop.
Uh,
Like all you really would have to calculate in order to understand the divergence of that diagram is the loop in the middle.
right. Right.
Yeah, so that's the idea basically of 1PI. Well, actually, let's do that. Could somebody
Is
send
that
me?
why? Is that why, like, when we write down its matrix element, we have two free indices, mu, because that's like
Yeah,
the gamma matrix coming in and going. Oh,
exactly.
okay.
Yeah. Well, I mean, you could think of it more simply in terms of the cubic vertex itself.
Right.
So the cubic vertex between a photon and electron, right? Two electrons and a photon will always involve a gamma matrix.
Yeah, yeah.
So when you have two of those, you'll have
Yeah.
those two indices coming out, and then you can contract them. So that's a nice way to think about it. There are too many tree diagrams on Google Images, so I'm just gonna,
Mhm.
for, for the benefit of people who want to follow this, I can take this logo now. Oh yeah, here's something cool. Let me extract this somehow. Did that work? No, didn't work. Let me copy image, paste it. Huh, didn't really work. Oh no, it did. Great. So you see there's this mess here.
Whoa. I thought we were doing the CFRC logo. This is a little bit too much.
But you see if you wanted to, you could cut out the CFRC logo here, you could cut it out here,
Yeah.
cut this out, cut that out, cut this out. These are all, you could cut this out and it's a two loop diagram.
Yeah.
You see? One
Yeah.
loop,
Yeah.
two loops,
Yeah.
cut this out. Tree level diagram, cut this out, one loop diagram. So anyway,
Jesus Christ.
this is basically what happens as you continue the series expansion of that object, gamma, right? you get terms like this. Also, it's the reason why Feynman diagrams are not the best way to do calculations at higher loop orders.
Mhm.
It's pretty well understood now that they're not the way to go. What is the right way to go is something that people are still trying to figure out. But yeah,
Is that the
One
Ornfeld
second.
methods? The
exactly.
One second. Does the like the loop diagram, does it like not expand in a like kind of symmetric way?
What do you
But
mean?
okay, so you have the same diagram within the same loop occurring within the loop and within the loop and so on. does it not expand that way, or like
No. So if you have a
or
loop
this
within a
is
loop,
like
that's like a higher order diagram.
yeah.
So you
Okay, you can
at
have this
one loop
stuff, but then
order, no, but at one loop order, you're never going to see a loop within a loop. You're only going to see one loop, right?
yeah,
So to order lambda, right?
yeah.
Okay, let's think about this. So this is a one loop diagram. I have two cubic vertices, right? Two cubic vertices give me couplings E and E. So I have E squared or alpha squared, depending on how you scale it. Okay.
Okay.
So to alpha squared order, I can't construct anything of a higher loop. If I want, okay, so say I put another line here. What did I introduce? I introduced two more vertices, two more cubic vertices, right? And that's going to be alpha to the power 4. Like this guy. This guy has what? It has one cubic vertex, two cubic vertices, 3, 4, 5, 6.
Okay.
So it's like alpha to the power 6. So this is much higher order than this, for example.
Okay.
Triangle diagram. So
I mean, that's what I was asking, right? As you go higher up in orders, okay, doesn't it have some kind of a symmetric expansion from like the basic tree diagram? Like, I mean,
not really, no, because
you could have like all kinds of patterns, but then like if you could like have the most symmetric, higher order expansion and then work from that, does that make sense?
Pratyut, that would kind of work if, like, say you were just talking about QED. Then to a
Okay.
certain extent, yes, you potentially could. But if you're going to like mix in, like if you're going to do any standard model calculation, right? Like if I have a photon can split into quark anti-quark, and that quark anti-quark can exchange a gluon, right? Then there's no way like your idea of symmetry can be
Oh, okay,
extended that
okay,
way,
okay. No,
right?
okay.
So if you're just like confining yourself to one singular theory, then potentially yes, like you could
Okay.
definitely weed out diagrams that do look like that, but not in
Okay.
general.
well, yeah, basically the point is that even loops are constructed by gluing together tree diagrams. Right? So let's try to understand that. Cut this in half. I have two tree diagrams that I've glued along this line. Right? So this whole unitarity method essentially comes from taking clever cuts of diagrams, and then there's what are called optical theorems that follow directly from unitarity that tell you how, like what the properties are of that thing. So you see this thing I cut here, I can cut here, I can cut here, I can cut here, I can cut here, right? And I can separate out the vertices. Now what Charinil was saying was that the photon has a vertex involving quarks and antiquarks. The photon has a vertex involving electron and anti-electron, positron. So in principle, you can glue together those different vertices in different ways if you wanted to. Right. So that's basically the question. You start by understanding what are all the tree level vertices that you have, and then you start to glue them together in different ways. Now, where does all of that come from? You can ask, right? Well, all of it comes from expanding the interaction Hamiltonian to various orders. Because what would I do here? I have cubic interaction between photon and two electron and positron, right? What does that look like? Where does it come from? Can you guess? So it comes from part of the electromagnetic Lagrangian, right? So let's see. So you need a term that goes like bar psi. Oh,
Mu.
exactly.
So you mean it like
That's
a
just the That's just the current, right?
Exactly. It's the current.
ah.
So you see, this is what? Psi bar, psi a, gamma at the vertex with an IE,
Okay. Yeah.
right? There'd be some pi stuff that doesn't matter, but basically you can sort of track what's going on. Like, recall that every propagator like this just comes from some free field theory. right? It's the Maxwell Lagrangian that determines this propagator, right? And all these interactions are just coming from some simple monomials of the fields.
Isn't that the gluon one? If you point, are you talking about the bottom right thing? Bottom left, sorry.
I'm just saying that you take this. I bet. Okay, I'm not sure that this is even electromagnetism.
No, that's
Yes.
the curly thing is gluons.
It depends on your notation, but oh yeah, I guess so, right? This is, I
Yeah,
think this is what
yeah,
they're denoting by electrons.
yeah.
But it doesn't matter much because all I really need to do if this is a gluon is have some index
Yeah.
here, some index here, contract them with something else, whatever.
You need
Right?
a
I have
DAB also, right, for the color factors?
exactly. So I have some. Well, no, I'd really have something like this. I would have F, A,
Yes.
Oh
B,
yeah, those structure.
C. Well, actually, no, I wouldn't. I'm not even. I don't even remember this very well because if it's so the problem with this is that these are not in the adjoint representation. They really are in the fundamental representation. That's why I need a T.
Yes. Yeah.
If there was gluons,
You have the structure
if this was a
constants.
gluon, then yes, right? If this was a gluon, then I'd have something like this. Then I would have F, C. Oh no. Yeah, C, A, B, although this is not the right notation for it. Somebody needs to go downstairs. but you get the idea, right? That you're going to construct these diagrams vertex by vertex, glue them together, and then the part that you need to deal with is the momentum part. You see, all of these are not just functions of their, say, color indices, and they have some spinor indices because you have these gammas, but they're also functions of space. Sorry. Right? So these are all functions of space, or alternatively momentum space. Right? And this is the part that makes it tricky to, I mean, this is what's interesting or non-trivial about these things is the dependence on these momenta. Otherwise, it's just combinatorics that determines what these diagrams are. In fact, we could deal with the theory of pure matrices. It's one of the simplest models of Yang-Mills theory, right?
Right.
They're
Yeah,
called
yeah.
matrix models. And then in those theories, there's no dependence on space at all. There's zero-dimensional theories. And you only have these graph combinatorics to deal with. So you're only dealing with these contraction patterns. And so that's like a simple way. You can understand ways of organizing perturbation theory through them, actually. There's something called a large N expansion that comes about because you know how to deal with them. But I mean, here, what's interesting and what's hard is a dependence on the momenta, which means that you could take a very simple theory like 5-4 theory and still have to contend with it, right? So what happens in 5-4 theory? I mean, you have no varieties of particles. You have essentially one kind of particle, right? And so the kinds of loop diagrams you're going to see look essentially very simple, right? They only have one kind of line. So something like this. Okay, well, I've cut off the P a little bit short, but as you can see, this is a 1-pi diagram of 5-4 theory.
Yes.
Why 4? Because I see 1, 2, 3, 4 here. Right? What did I do? I took an X and then I tied the top. Right? So now, the nice thing about this is that you ampute the external lines. By amputing them, that means that there's 2 propagator terms that I just omit. What is the effect of that? Remember when we were doing the Dyson series expansion, we had terms that went like propagator, matrix element of the interaction Hamiltonian, propagator, so on, right? Ampute the propagators, you only really have to deal with the matrix elements of the interaction part. And if you recall from our quantum mechanics examples, that was the stuff that was diverging when it diverged. Right? It was the matrix elements of these guys. Okay, you might have propagators in between though, right? So the propagators in between really are the analog of these loops. So remember we had something like P V hat p times I over something times p within an integral. That's the part that we're trying to deal with here. So, I mean, I don't know if you guys all saw this recording I made of these divergent terms in the quantum mechanics example. But yeah, I mean, it might be instructive to go over real quick, just because it's essentially the kind of thing that's going to happen now. Okay, like the reason that those diagrams diverge is the same, or those integrals diverge is the same reason we're going to meet here. It's just going to be in higher dimensions. So let me see if I can open my divergence notebook. Okay, so I'm going to share a different screen now. It's going to be great. So remember we had this table in the 1D case. The claim was that this converges and this diverges. What does that mean? So it means that if I integrated this as a function of p, right? So you see big E here is small e, and I have the I epsilon. And you get some inverse hyperbolic tan function. Mathematica gets it, I don't. And what I do is I look at the upper bound of the integration, I set p to lambda, and then I expand around lambda set to infinity. And you see it's fine. I only get terms that drop off, like 1 over lambda cube. So as lambda goes to infinity, they all vanish. Okay, that's nice. Then here's the thing that would diverge. Where did it come from? It came from this times itself with the propagator in the middle, right? That's how we get this. You see these, there's two factors of C1. There's two of these P minus P things. That means there's two of these factors. So these are vertices. So all the Feynman diagrams in quantum mechanics are essentially sitting on a line. There are no loops because there's no space, right? It's just time. So you have a line, and then you have different vertices along the line, right? So now we have two vertices, right? And you see we have this integral.
So it's basically some sort. You're just saying that there is like a discontinuity between the initial and the final moment, right? I mean the initial and the final state, because yeah, that's like where you have the sign flip. So that is what that is why you have to you need to amputate both the
It doesn't, I mean, there isn't any discontinuity. It's just a term in the expansion. So like the expansion goes like line, no vertices, plus line, one vertex,
okay,
plus line, two vertices.
okay,
There's going to be three. But you see, two vertices is already a problem. Two vertices, internal line, that's what's diverging in quantum mechanics.
okay,
And that's what we're dealing with here.
okay.
Right? So P is like one dimension, it's just, like flowing along a line. Then you imagine I have two of these vertices being dropped. And I'm trying to calculate what's going on there. So
Sorry,
here,
could you just repeat the last step? My sister came into the room and she
that's right,
made
sure.
quite some noise.
No worries. Let me see if I can draw a little bit. So insert graphic, is it? No, let's do graphic, new graphic. Great. Drawing tools. Anytime now. This is pretty frustrating. But I think that this is worth going through a bit slowly, and then next time we can talk about. Anyways, since the aim for today is understanding where one divergence comes in one diagram in 5-4 theory, and then understanding what we do to remedy that, and where the how the rest of it should work. So great. Where's my? Yeah, you see, so this is what happened. That's what happened. Right, so this is my first order term, right? I'm just going to draw it, and then we'll talk about the meaning of these things a bit better. Sorry,
Sure.
this is 0th order term essentially. And then to first order, I drop a vertex in here. A vertex looks like this. Sorry, make it a bit bigger. Right, so I have a line with a dot. Then I have 2 of these dots, and that's when I get into trouble. And 1 here, I have 2 here. Right, so what's the 1 dot thing? It's this. PVP, it's just a constant, doesn't matter. Second order thing is I have this.
Sorry,
times
so does
itself.
that symbolize the vertex?
Exactly, yes. That's what symbolizes the vertex. The vertex
Okay.
is the matrix element of what we're calling V hat. V hat is the interacting part of the Hamiltonian or the potential.
Makes sense. Thank you.
No problem. So then to second order, what we're going to have is some propagation between vertices. And that's what this function denotes. And the fact that we're summing over all momenta in the middle is the integral here. And so the one that we're concerned about is what happens when the potential is a derivative of a delta function. And that's what we're evaluating here. And here, the cool thing is that, okay, you get some nasty function. But you see, when I take the result of this integral and I plug in p equals lambda, I see that it's linearly diverging. It's a function of just a linear function of lambda. So when I take lambda to infinity, it just goes to infinity. It doesn't matter too much what all this stuff does, but it doesn't do anything good either. Great. So now in 2 dimensions, right, when we had a 2-dimensional potential, we had a delta squared of x, and we were wondering what happened to this term again, right, to this kind of term. And so there we see that we have a vector here, p squared, instead of just a scalar p, like we had in the 1-dimensional case. So what we do is we just write this vector p. Sorry, I couldn't get the notation to come out with a hat or a vector sign on top, but this is a vector. I decompose it in polar coordinates. Now p here is just a scalar, like it was above. And my integral becomes this thing, right? So I have the cosine here that I need to integrate over. So I first do the angular integral, get some messy rational function. Mathematica is bad at simplifying square roots for whatever reason. I mean, you can give it a bunch of prompts to do it, but I always forget how to do that. But anyway, I just cancel it by hand and then plug it back in. So this is a p power 4 here, but then I have a p outside. It all goes under a square root, so this becomes p squared under the square root. Do the integral, get something horrible. It's not as bad as it looks. It's just that Mathematica is struggling with canceling things again. This cancels with this, right? This cancels with this, and there's only the arctangent left. Doesn't matter. I'll just take epsilon to 0, p to lambda, and expand to 4th order. I get this floor of argument thing, some integer. Doesn't matter what it is. It's not diverging. Right? This, however, is a problem. Because when I take lambda to infinity, this goes to 0. And as you know, log of 0 is a problem. So yeah, this is basically what I meant when I was saying that this diverges logarithmically. So
I have a question.
yeah.
I do remember briefly reading about this in Pascal and Schroeder, but I don't remember the exact formal argument here. But like the fact that a divergence is logarithmic means that the divergence is really slow. Is that one of the reasons why renormalization is a valid procedure, because it's a logarithmic divergence only?
No. It's just that renormalizable theories have typically tend to have logarithmic divergences. So not all divergences are the same. We'll come to this later. But okay, so what are you interested in doing? What you're interested in doing is redefining couplings in such a way that you can capture the effect of these divergences into them, right? So we're talking in terms of divergences because we're looking at bare couplings defined at the cutoff scale. you could do this somewhere else, right? With our knowledge of how the RG works, you could do this somewhere else, and the procedure would be the same. The point is, the momentum dependence of the coupling can be captured into a redefined coupling, so that, in
Right.
fact, the Lagrangian doesn't have to look any different.
Mhm.
All you really need to do is define it with respect to a new coupling. This is actually different from having to define new terms in the Lagrangian.
Right.
Okay, you could say that even here with counter terms, I'm introducing new terms in the Lagrangian. But note that if I have new terms, they're all just given by redefinitions of the old terms with renormalized couplings.
Mm.
So in form, they're completely identical to the terms I had before. That is what it means for a theory to be renormalizable. In a non-renormalizable theory, there's no unambiguous way of redefining the couplings in order to capture the effect of the new terms being generated. The new terms are generated as counter terms that cancel divergences in diagrams coming from what you already have. And that's where, life gets a little bit harder. But again, in those cases, divergences tend to be power law. They're not logarithmic.
Okay.
And there's something much more important about logarithmic divergences, right? So we're thinking now just in Euclidean signature, where we can define a cutoff universally. But life is not like that. We're in Lorentzian signature in space-time. Now, what is the difference between log of S and log of T? Where S and T are Mandelstam variables.
Oh, log of S is wait.
They basically have minus, there's like a
Yeah,
minus
yeah,
between them.
yeah. S is always positively defined. T isn't.
Exactly, which means that the difference in the logarithms is some phase, I pi or something like that,
Yeah.
right? So it's something plus I pi. Who cares about the additional I pi? It doesn't contribute. What's the difference between S cube and T cube? They're very different now, right? One will grow and the other will start to decay. So if you have power law divergences, I define running couplings with respect to S, T, U, right? And you want them to decay at high energies. But what does that mean? You mean as a function of S or as a function of T? Well, you
I'd
want it to be
ass-
both.
I'd assume it should be a function of S.
Well, no, it should be a function of, it could be a function of all of them,
Oh,
right?
okay.
Because STU form like a basis in some sense for all your kinematic invariants, right? The point is that I need running couplings to be ones that have decent high energy behavior in any channel. They should respect crossing symmetry, in fact, right? But now if I redefine my coupling in a way that depends on some power, I'm immediately in trouble, right?
Right.
So I could say, oh, I defined a nice coupling which as a function of S goes to 0 as S goes to infinity. But now as a function of T is just, you're gone. Like, you're growing, right? So this is basically another way to see that power law divergences are very different from logarithmic ones. So yeah, that's a little bit more of a subtle point, but it's something that took me a very long time to realize, and I think it's a very important one. Anyway, going back to what we have here, so we're comfortable with understanding that there's some integrals or momenta that converge and some that diverge. So obviously, I don't know how to do this integral and get this answer. I mean, I have to go back, look at some tables and so on. And I honestly don't want to do this every time I deal with the theory. So let's see if there's better ways of going about our lives here. We're concerned with how this thing behaves, right? How this function behaves at high p, right? So actually, let's just look at this. We have 1 power of p in the numerator, 2 powers of p in the denominator. This is already giving us a lot of indication of what's about to happen. Why? Because I can expand this. Sorry, series. This as a function of p. And unsurprisingly, right? when this computes, the leading term is going to be 1 over p. Right? It's going to be sec theta over p. dp over p, what's the integral? Log of p. So you already know that this is a logarithmic divergence. You don't really have to do much, right? So you could do the same kind of test above. Let's go back to the 1D example, right? Why was this going to be safe? Again, large p, I can ignore everything over here. It's dp over p squared, which is like what? Some inverse function of p is fine. You don't have to care, right? Here, I'm again in trouble because it's a toss-up. You know, who's going to win, numerator or denominator? So now I actually have to go do some work to find out. Right? Well, actually, no, it's not even that much work because this is p squared over p squared dp, which means it'll grow like p. And that's exactly what happens. The leading term grows like p.
Isn't this worse because you not just have one term that grows as p, but you have another term that goes as log of p, right?
Sure, you're right. Yeah, because if I expand this, there's going to be another one. So yeah, but the leading divergence, the most divergent term is going to be p, which is already telling you that it's bad enough to have to deal with, that you're going to have to deal with, right? And so that's exactly what we do in field theory to determine the superficial degree of divergence. So let's go back to the example that we want. Right? So now, what is this going to be? Well, one day we'll go learn how Feynman rules work, but for now I'm just gonna write down the answer. It was 24, was it? It's 24 symmetry factors. I don't know. There's some number here. That's just a number. It's probably 2. Yeah, we'll have to deal with symmetry factors one day. So you have D4K. Sorry, 4K over here. And then you have some 2 pi to the power 4. And really, you just have one propagator going in a loop, right? And we know what the form of the propagator is. It's going to be I over k squared. Now this is really a 4 vector. Remember that. I don't think this is the best notation for 4 vectors. Just m squared again. We're gonna look at this. I epsilon. Right? So this is the form of the propagator. Let's go to Euclidean signature because it's easier to do the calculation there. And for our purposes, it's fine. So let's just go to Euclidean signature where now we have just Euclidean momenta. So I'll denote indices in the Euclidean space with just Latin.
Won't the I cancel out?
Yeah, there's no I. You're right. It becomes minus. Yeah, there's minus I. This just becomes 1. There's going to be, I think the I outside remains, but we're just going to look for the divergence. Let's figure out where the I's go later in life. Why are we going to Euclidean signature? Well, in Euclidean signature, you can make sense of a high momentum cutoff. Right? Okay, so this is a simple fact about Euclidean versus Lorentzian. K squared equals constant. What does that mean in Euclidean signature? What does that draw? Ki equals...
Kind of hyperboloid?
Huh?
Like a hyperboloid or something?
No, a sphere. We're in Euclidean signature.
Right. So, yeah, that's just...
So the problem with Lorentzian signature is that it's a hyperboloid. really inconvenient thing to think about cutting off. Like, what is the point? You have a hyperboloid with that's like that has this big, this slanted or this slanted. It's both infinite. It doesn't matter. So you see, you can't regulate in Lorentzian signature by saying that k squared equals something. Right? So instead you go to Euclidean signature where I can really put a cutoff. Right? But how do I put the cutoff? I put a cutoff on a radius. So I do I lambda 0 over 2 times 1 over 16 pi squared. And I have an integral from 0 sorry, k squared. So it's easier to just deal in terms of k squared itself as a variable. K squared plus m0 squared. Okay, if we expanded this out, it would be dk, 2k dk, right? But fine. We see that it's going to be a logarithmic divergence anyway. Right? Because as a function of k squared, what happens? Or as a function of k, what happens?
Won't it be a linear divergence squared over k squared?
Yeah, won't it be linear?
Oh, no, sorry. It's going to be linear in terms of k squared. It's going to be quadratic in terms of k. It's going to be quadratic in terms of k. You'll also have a log term, but that's a separate one. So, okay, this is going to diverge, right? Basically, and you're right. It should be quadratic because it's a mass that we're renormalizing at the end of the day here, right? Something that goes like mass squared. So let's see what the result of this integral is. I'm going to do a quick mathematical calculation. So we're integrating. I mean, I know that this isn't a hard integral. I just don't like getting factors wrong.
Sorry, I just want to confirm one more thing. Because you're integrating with respect to k squared, shouldn't the upper bound just be lambda, or will it still going to be lambda squared?
It's still going to be lambda squared, right? Because the cutoff is still k squared equals lambda squared. X plus m squared. Yeah, let's see what I'm going to get. Okay, so this is going to be all this stuff times lambda squared minus not squared log use Mathematica's log or latex's log. So squared plus m squared over m squared. Yeah. So this is what you're going to get. Oh, and all of this is m naught, basically. And as you can see, since lambda is going to be taken to be large, we can really ignore this extra m naught squared here. It's going to be much larger than m naught squared. So whatever, it's this plus stuff. That doesn't matter too much. So now what's the moral of our story when we were trying to understand renormalization before? It was basically to say that we will redefine couplings in order to absorb the cutoff dependence. So which is the coupling that's relevant here?
Not
Wait, no, m naught is a relevant coupling
I'm
here.
not.
Exactly, yeah. Very good. So we're seeing an example of mass renormalization. Right? So basically what we're going to have is an observable that we have to identify. What's the observable? It's the inverse of the propagator, right? But the full renormalized propagator. So the one that sums over all 1pi diagrams, right? But we're only expanding it to first order in lambda naught, right? And so that object is basically going to be, well, I don't know what to call it, inverse propagator. Equals p squared minus m naught squared. Sorry. Minus all this jazz, right? The naught times 32 pi squared. So there's going to be a lambda squared minus m naught squared log of lambda squared over squared. Right? So what's the inverse propagator usually? It's like p squared minus m squared renormalized, which means that all of this is going to be our renormalized m squared rather, right? You just identify it as that. So
Is it
basically,
an issue that the renormalization is dependent on the cutoff?
Hmm?
Why isn't it an issue that the renormalization
no,
is dependent on
because
the cutoff?
you want your cutoff, no, you want your renormalized couplings to depend on some scale.
Yeah.
Here, that's the cutoff scale. Yeah, okay, that's because we're talking
I
about
think
bare couplings.
I think even when we wrote the Lagrangian, I think we made the assumption that the scale is one, right? Of the coupling constant of the Lagrangian itself is one. So I think that reflects. So you just have the
No.
order, the
So
mass of the
there,
particle just showing as
no, we
in.
still have coupling being lambda there. Oh, sorry, the cutoff being lambda there, because
Okay.
we wrote bare couplings. The coupling of the kinetic term was 1, and that's why you have p squared appearing without any coefficient in front of it. That's the difference. Anyway, what do? We differentiate this thing with respect to lambda, demand that the answer is 0. Right? So after some effort, we would get that 0 equals minus d m naught squared over d lambda minus whatever. This lambda 0 over 32 pi squared, right? And then you're going to have 2 lambda minus m squared. Well, yeah, you're just going to have 2 lambda minus 2 over lambda m squared, right? Have this. Sorry, that's not an equals. Right? So from here, we're interested in the logarithmic divergence of m squared, as in the lambda d lambda. Basically, to say that we can rewrite this equation as, just take lambda to the other side. This is just a convention, but this is usually how you tend to write RG equations. As in you're differentiating with respect to log lambda instead of lambda itself. 0 over 16 pi squared times minus m naught squared. You just take the 2 also to the other side and you'll be fine. Right? So this is our RG equation for the running mass, essentially. So this is like the mass renormalization. And you see, it makes sense because this diagram would only know about the propagator. Mass renormalization now depends on the coupling because the coupling entered into this diagram too. So with this intuition, can we guess what the diagram for the couplings renormalization should look like? Remember, the bare coupling is just the X diagram, right? The vertex.
A tree.
Hmm?
A tree.
No, it wouldn't be a tree. We would need loops in order to. Again, we're talking about one PI diagrams. If it's a tree, then I just cut it. Then we're back to where we were. So you see, I just glue the trees together though to form a loop. So it's gonna be like, I'll just pull it off.
So you don't have a propagator in the middle.
Yeah,
You
yeah.
have a loop.
Let's see how it looks. This is how it looks. Come on. I lost the screenshot. And this is what we'll deal with next time. Okay. This is really struggling. Yeah, my computer's hanging, but basically that's homework, I guess. Technology is not cooperating with us. Anyway, does this connect well for you guys with the stuff that we'd seen before?
Yeah, pretty much was able to follow.
It really helped when you just drew the parallel back to the quantum mechanical case with the matrix
Yeah.
element.
Yeah,
That
exactly.
made the connection way more clear.
I'm glad because that was the point of all of that. And when we come back to the Dyson series, it'll be hopefully even more clarifying, like when we derive the Feynman rules, because it's really the same thing that's happening. And now it's just that our interaction Hamiltonian is going to be these potentials involving things like phi4 or whatever, right? And then it just generalizes from there. It can really go all the way to like QED, and then you can start to deal with other annoying things like gauge fixing, ghosts, etc. But at the back of your mind, you have this stuff pretty clear. So yeah.
I think we can stop.
Yeah, I mean, do you have any other questions before we? Okay, cool.